Recall in the last video we discussed how we really needed to get a better handle on sampling error. And to do that, we started thinking about how samples would vary from sample to sample, which is something called a sampling distribution. Then we went one step further and said, well, we really care about the sampling distribution of the sample means. That is, how does X bar vary from sample to sample? And we saw that the shape becomes normal, the center kind of stays where it was, but the spread becomes significantly smaller. So we want to formalize that and add some caveats and conditions for it in something that's a very big deal called the central limit theorem for means. Now you're going to learn two central limit theorems, and they are very, very, very important to us. They're the hypothetical philosophical foundation for the rest of the course. So it's talking about how if you have a population of size capital N that has a mean of mu and a standard deviation of sigma, and you select samples of size little n, then this entire theorem is how we expect that distribution to work. Now, we have a few conditions to set up how this is going to happen. Condition number 1 and number 3 are actually tied together. Number 1 says you need to have a random sample and independence. So, well, of course. I mean, in statistics, we always say we have random samples that are independent. Otherwise, we're kind of in big trouble. But of course, in real life, it's kind of tricky to ensure you're getting a perfectly random sample and perfect independence. But for our purposes, we'll say we did it. Of course, in our die example, it was no trouble at all. Dice are independent of each other, so that was no big deal. All right, now how do you ensure independence if you're taking samples and you're not replacing them? That's this part down here. And the answer is, well, you can do it more or less as long as you take a really small sample in relation to your larger population. So bear with me, for example, imagine you want to take a scoop of 30 M&Ms. Okay. Now the M&Ms are people, they're a metaphor. So people, different colors, shapes, sizes. You can throw peanut, plain, whatever. Throw any size in there you like, and you want to take a little scoop of about, I don't know, 40 of them. So you want to take your scoop of 40 M&Ms. If you take it from a fun size bag that you buy at the gas station, those 40 M&Ms would be a lot of M&Ms, and you'd have very little left in the bag. So if you don't replace the 40 M&Ms, if you do this without replacement, you're fundamentally changing what's left in the bag, and that would not be independent, right? You would lose independence up here. That would be bad. So what they say here is that, look, it's okay if you don't replace them, just as long as you take it from a really, really big bag. Just as long as you take it from a population that is at least 20 times larger than the sample size. In other words, your sample size is less than or equal to 5% of your population. Now, what do I mean by that? Again, imagine your scoop of like 40 M&Ms from a little fun-sized bag. That wouldn't be good. But what if you were at the M&M factory and they had a huge vat of M&Ms? Then you take your little scoop of 40, you're not really affecting what's left. Well, I mean, not by much, let's put it that way. You're affecting it so minimally that you basically can ignore it. And that's what this part is saying right here. So number 1 says they've got to be random sample and independent. And independent without replacement is a little bit hard to come by, and that's this part down here. If you're going to do it without replacement, then make sure you're taking a small scoop from a big vat. Of course, the scoop is a metaphor. Make sure you're only sampling a small group of people from a large population. So if you're going to talk about the average score on the SATs, you only want to have a group of about 40 students. You want to compare one group of 40 students to another group of 40 students to another group of 40 students. You wouldn't want to do samples that are so huge that they are larger than 5% of the population of all students that take this test. All right. Those two conditions kind of are tied together. They're linked, right? So the bottom part is to ensure independence if you don't have a replacement. But then the other side happens, which is you don't want your sample to be too big. That's this part. But you do want a decent size sample. And how decent is decent? Well, for our purposes in our course, we're going to stick with the 30 rule of thumb. Namely, that the distribution will be normal as long as either they tell you it's normal, right? Either the population distribution is normal, given, right? This will be given to you in the problem, or the sample size is large. The other way they could do it is not only given in the problem, or via normal probability plot, right, from section 7.3. Okay, so either it's going to be normal given or normal probability plot, or the sample size is large. And for our purposes, large, quote unquote, is bigger than n greater than or equal to 30. I'm going to put large in quotes because, of course, 30 is not that large, but it's large enough for our purposes. All right, there we clarified that up. And then I also threw in this little note right here. So this little condition, this condition ensures independence if the sample is without replacement. So if we have these three things, and to be honest with you, we usually assume 1 and 3 kind of automatically, more or less for most problems. So that leaves us mostly checking number 2, that n is greater than or equal to 30. So if we have those three things, then the distribution of the sample means x bars is described as follows. Shape will be approximately normal, no matter what the shape of the population distribution was. So even if you had a skewed distribution originally or a uniform distribution originally, like we had back here at this one, no matter what the shape was, when you take the sampling distribution of the sample means, it will be normal, more or less, at least for our purposes. Then the center will have a mean, the center is the mean, which is equal to mu. So the mean of the x bars, that's the symbol for it. So it's the mean of your means. So you're not looking at the individual data, you're looking at the x bars from different samples. And the center for all those samples will be equal to mu. That's why if you look at these graphs here, we kept coming up with 5.5 as basically our center. That's because it was the center for all the x bars, just because it was the center for the mean for the original data right here. And then the spread. So we can see that spread is changing. That was the contrast part from this problem here. So the spread is getting smaller, and there has to be a formula for it because mathematicians love formulas. It's called the standard deviation of the sampling distribution of the sample means, which is a lot to say. So instead of that, they call it the standard error of the mean, which is SE of x bars, standard error SE x bar, standard error of the mean. SE of x bar, that first notation is how computers write it. So computer programs can handle this notation. By hand, you can handle this, which is the standard deviation of the x bars, right? The standard deviation of the sample means. And the formula for it is sigma divided by the square root of n, where sigma was the standard deviation and n is the sample size. Now keep in mind what this means. We now have standard deviation, which is for the population, and standard error, which is for the sampling distribution. And they're not the same thing. And you're not allowed to call the standard error the standard deviation. I mean, unless you call it the standard deviation of the sampling distribution of the sample means. That's what it is. Well, unless you're going to say all of that, then you have to say standard error. And you can abbreviate it SE of x bar or sigma sub x bar. And that is the spread for your sampling distributions. So let's figure out what it was for our two values that we already had. We had n equals 2 and we had n equals 6. Let me type those up 1 second. All right, there we have it. When n equals 2, the standard error of the x bars, the standard error of the means, sigma sub x bars, the other notation for that is sigma divided by the square root of n. That's about 2.872 over the square root of 2. Let me just write this formula in one more time. Sigma over the square root of n. Let me grab the calculator and clear this. So I want 2.872 divided by the square root, so second square root of n, which was 2. And that's about 2.031. Okay, now let's do it again for 6. So it's going to be the same calculation, except it's going to have 6 down here in the denominator. So we go here in second entry and change this number to 6. Oop. There we go, 6. And we got 1.172. So 1.172. All right, I'm going to go label those on the graph. I'll be right back. And there we go, I have them labeled right here. So this curve, this gray curve, has n equal to 6. The mean is 5.5, which is what we said it was over here. And then the standard error is 2.031. Whereas the black curve has n equal to 2, which means the mean is still 5.5, but the standard error is now about 1.172, which backs up what we said here, which is that the black curve, where n equals 2, oops, nope, I have them backwards. Look at that. I'm losing my mind. This one's the 1.172, of course, because it's got smaller spread. There we go. And this one has the bigger spread. There we go, 2.031, I think. Yeah, 2.031. There we go. So the black curve has more spread, larger standard error than the gray curve, which has smaller spread, so it's a smaller number for standard error. All right then. So what do we want to say about this? The larger the sample size is what I was just saying a second ago. The larger the sample size, the smaller the spread, right? The smaller the error. So let me write that out. All right, so as your sample size increases, for your shape, there's two options. Either it becomes normal if n becomes greater than 30, if n is greater than or equal to 30, or it stays normal if the original distribution was already normal to begin with. So if your population distribution is normal, you don't need a sample size of 30. You could have a sample size of 2 and it's going to be normal. But if it wasn't normal to begin with, then it will become normal for our purposes in this course if n is greater than or equal to 30. Then the center will stay consistently at mu of x bar is equal to mu. And the spread, which is the standard error of your x bar, which is sigma sub x bar, which is sigma over the square root of n, will get smaller. Because as n increases, that means your denominator is increasing. And if you increase the size of your denominator, then your overall number will get smaller. In other words, the larger your sample size, the smaller your error, which backs up what we said way back at the very beginning, right here. We said in general, the larger the sample, the smaller the sampling error. And that's what we're seeing here. The larger your sample, the smaller your standard error. And standard error, if you will, is a measurement to some purposes of that sampling error.